All right, so this is chapter 9. We're going to do it all in one day. It's going to cover transformations. So, you know a couple of vocab words first. First one is pre-image. That's the original figure in a transformation. Okay. The next one is image. That's after you do the transformation. The first transformation we're going to talk about is translation. So a little hint to help you memorize this is translation has SL in it, and that's a slide. SL is also in slide. You can move it up, down, left, or right. If you look at below, there's some notation. You see D, E, F, G, and then you see D prime. Okay, see the little apostrophes? That's going to be after you've already moved it. So let's look at our picture to the left, and you have the blue object, which is your pre-image. Okay, we want to see how that has translated to the new image. Okay, so it looks like it went left and down. So you can pick any point you want, it really doesn't matter. Let's just start with D, and let's see how much it moved to the left. So it went 1, 2, 3, 4, 5 spaces to the left, and it went down 1, 2, 3. That'll work for any point, and you can check multiple ones if you want. So now we're just going to write like a generic coordinate point for this whole transformation. So x went to the left 5, so that'd be minus 5, and y went down 3, so that's minus 3. Okay, we're going to do the same thing, so we're just going to practice that. First of all, you need to figure out which one is your pre-image. So find the one without the little apostrophes. So we're going to start with the blue object. And you can start from any point that you want. So this time we'll start from S, and let's just see how much it moved to the right and then down. So we were going to the right 1, 2, 3, 4, 5, 6, 7, 8 to the right. And we're going down 1, 2, 3, 4, 5. So let's write our coordinate again. So we went to the right, so that's going to be addition. So x plus 8, and y still went down, so it's going to be y minus 5. Okay, go ahead and try the next one on your own. This would be a good time to pause the video and then play it when you're ready to see the answer. Okay, so first of all, find your pre-image. It's the one without the little apostrophe, so it's in the top one. Start from any point. I'm going to start from T, and it looks like it's going left and down. So it went left 1, 2, 3, 4, and down 1, 2, 3, 4, 5. So your coordinate should be x minus 4, so we went to the left, and y minus 5. Okay, this is pretty much the same concept, but we're going to go about it a little bit different way. They're giving us the coordinate point, and we're going to actually do that transformation. So the object shouldn't look any different when we're done. It should just look moved. So we're going to go to the right 3 and up 2. It doesn't matter which point you start from. We're going to have to do this for all 3 points though. If it helps, you can label them. So we're going to start from this bottom point, and we're going to move to the right 3 and then up 2 and plot a point. And do that for the other 3 points as well. So move to the right 3 and up 2. Right 3, up 2. And then connect that. It should look like the exact same size and shape, just translated over 3 up 2. Okay, go ahead and try the next one on your own. Pause the video and play it when you're ready to see the answer. Okay, so we're going to do the same thing. We're going to move to the right 5 and down 3 for this one. So just start from any point, right 5 and up 3. Or sorry, down 3. And pick another point, right 5, down 3. And continue to do that from all the points. And your shape shouldn't look any different in size or shape. It should just look moved. So the whole thing has been translated to the right 5 and down 3. Okay, this is 9.2. This is reflection. So a good way to remember this is reflection has FL in it, and flip also has FL. So we're going to be flipping things. First thing we're going to do is reflect across the y-axis. So it's all about the y-axis. You might want to highlight that, or just focus on the y-axis. Okay. So basically, everything that happens on one side should happen on the other. So if you look at B, it's a distance of 3 units from the y-axis. So my other point, my B prime, should also be 3 points from the y-axis. Now when we go to plot A, there's a couple of ways you could do this. We could count the total distance A is from the x-axis, or the y-axis, or we could also just count the distance from A to B. So I think it's easier probably just to count in between A and B. There are 4 spaces there, so go over 4 from the other B, and that'll be your A prime. And same thing for C. So C is a distance of 1, 2, 3, looks like 5. So we want to go over 5 spaces on the other side. We're reflecting across the y-axis, so everything is in relationship to the y-axis. And again, your shape shouldn't look any different in shape or size. It should just look reflected or flipped across the y-axis. Let's do some more investigation with the actual coordinate points. Okay, so again, we're flipping across the y-axis. It should be the same distance from the y-axis. So let's look at A. A is to the left 2 and up 3. Okay, so the coordinate point A prime is positive 2 up 3. So what happens? Well, when you're flipping across the y-axis, the y value stays the same, and the x changes. Okay, so both going to be 2, 3, but one's going to be, x is going to be negative, and the other one's going to be positive. Okay, so now we're going to talk about reflecting across the x-axis. It's very similar to the y. So let's go ahead and look at those. If you look at B and B prime, they're both 1 unit away from the x-axis. B is over 1 up 1, and B prime is over 1 down 1. So what happens here is that the y-axis has now changed. The x-axis doesn't change. So let's kind of summarize that. If it's across y, y stays the same and x changes. If it's across x, then x changes, or sorry, x stays the same and y changes. So the very last one, we really don't even need to use the picture. So let's just see if we can come up with the answer. If it's across the x-axis, the rule is don't change x. So x is still going to be negative 3. We want to change the value of y. So it would be negative 3, positive 3. And we can go over to the picture and we can check that. So if you look at C, it's going to be left 3 and down 3, but C prime is left 3 and up 3. Okay, reflections across the line y equals x. So the red line is the line y equals x, and everything, like if you look at A and A prime, they should both be the same distance from that line. It's pretty simple. If you look at the values of A, one is over 2 up 4, the other is over 4 up 2. So the basic rule here is that the x and y just switch. So our new point is 4, 2. Okay, so we already have the B coordinate. We can see that B is over 1 down 3. So what should the coordinate be for B prime? Well, if it's across the line y equals x, the rule is just to switch them. So it should be negative 3, 1. And let's go ahead and plot that just to make sure that it looks right. So if we go to the left 3 and up 1, it looks like B and B prime are about the same distance from that line. So it looks like we did all right there. Let's go ahead and do the same thing for C prime. So if you want to pause it and try it, and then play it when you're ready to see the answer. Okay. So C is located at negative 1, 2, which means that C prime should be located at 2, negative 1. You just switch them. This is for y equals x. So let's plot that point. Positive 2, down 1. They look the same distance from that line. Okay, so we're going to reflect this whole thing across the line y equals x. So let's write out our coordinate points first for A, B, and C. And A is over 5 and up 2. B is over 2 and up 8. C is at 0, 0. And then let's write what the new coordinate point should be. So A prime, the rule for across y equals x is just to switch them. So this should be 2, 5. B prime is 8, 2. And C is still going to be 0, 0. So C prime and C will both be on the same place. So there's C prime, A prime, B prime. Go ahead and plot those points. And they're overlapping, so it might be hard to see, but when you're all finished, you'll see that it has been reflected across the line y equals x. And we can even draw the line y equals x just to make sure that it looks right. So there's our object. It looks the same, it's just been reflected. And if we draw the line y equals x, you can see that it was reflected across that. So far we have the rules. If you're reflecting across y, you leave y alone. Reflecting across x, you leave x alone. And then you just change the opposite sign. And then for y equals x, you just switch places. Okay. So we're going to move on to 9.4. This is symmetry. All we're going to do is just see how many lines of symmetry that each of these objects have. So if you look at some of the examples, the letter F, it doesn't have any. Think about trying to fold these things in half or fold them multiple ways. So if you fold a triangle, you can fold it one way. Unless it's equilateral, then it might have more lines. So let's just go and try these. The butterfly, how many lines of symmetry do you think that has? You should have 1 line of symmetry for the butterfly. The next one is an equilateral triangle. So how many lines of symmetry would this have? You can fold it that way. So it has 3 lines of symmetry. That would only be true for equilateral. If you look up at the top example where it has 1, for an isosceles it's only going to have 1 line of symmetry. Okay, the next one, it's a circle, but it has a design. If you just have a plain old circle, it's going to have infinitely many lines of symmetry. But because this has a design, we have to pay attention to that. So just try to cut it as many ways as you can and think about folding it over. And if it looks the same on both sides, you should be good. So we can cut on all those lines. We can also cut in between. And it looks like we have 6 lines of symmetry. Okay, and the clover, just try to fold it in half. It's kind of like a rectangle, or like a square. Okay, those are all the lines of symmetry that has. So just try to think about folding it. Next thing we're talking about is point symmetry. So if something has point symmetry, you'll be able to rotate it around 180 degrees and it's still going to look exactly the same. So if you need to, you can literally draw the picture and turn your paper around. Just try to flip it. If it looks the same, then it's going to have point symmetry. So. Okay, so when we drew the letter S and we flip it around, it still looks exactly the same. So does that have point symmetry? Yes. Okay, let's look at each one of these. So this first shape, do you think it has point symmetry? Do we turn it on? Okay. So try to turn it around. So it's going to have a yes. Oh, I thought you was going to turn it. Okay. The next one, try to turn it around. Does it look like it would be the same if you turn it around? Yes. So that has point symmetry. Go ahead and try the next one. It should also be yes. And the last one is as well. These are all examples of point symmetry. Okay. So if you can turn something around and it has 180 degrees and it still looks exactly the same, then it has point symmetry. Okay. All right, 9.3, rotations. So when you're rotating something, you're just turning it so many degrees. Okay, so think turn when you hear rotation. Okay, so we have up here, we have our pre-image, the letter T, and we're going to rotate it 90, 180, and then 270. Okay, so go ahead and try to do that on your own. You might want to pause the video and then play it when you're ready to see the answer. Okay, so below we are going to rotate. Notice that we're starting in a different quadrant, so it's going to be a little bit different from the top one. Yeah. So we're going clockwise, so now that I'll put this in the quadrant, there we go. Okay. And then it's going to bump over to the next quadrant. Okay. Alright, 9 and 5 is all about dilation. So if you've ever been to the eye doctor, they dilate your pupil. So something's going to get larger. It can also get smaller. It's going to have the same scale factor. That's the key thing. We've been talking a lot about scale factor. All the sides need to increase by the same amount. So if you look at this example, if you look at the coordinate points, in the pre-image, the vertices are at 1, 2, 3, 2, 3, 4, and 1, 4. Okay? When this was dilated, the new coordinates became 2, 4, 6, 4, 6, 8, and 2, 8. So what do you notice happened between the old coordinate and the new? It was multiplied by 2. So all the sides should increase by the same amount, but also the coordinate points are going to have a relationship as well. Okay, so let's practice finding the scale factor of each dilation. This should be pretty simple because we've been doing this in quite a few chapters recently. So let's put these in order from the blue object to the black one. So count the number of units on the blue side. So there's 2. And then count the number of the black. 6. And we always want to reduce it. So that reduces to 1/3. Okay, so let's do the next one. Count the number of sides. You can pick any side, it doesn't matter. So there's 2 spaces again there. Just make sure that you're matching up the corresponding sides. Okay, that one again is 2, 6, and when you reduce it, you're going to get 1/3 again. Okay. Go ahead and try to maybe do a couple on your own, and then if you need help, just play the video again. Okay, so we're going from blue to black, so we're going to start the bigger object this time. So count the number 2, 3, 4. And the black one has 2, which reduces to 2 over 1. Okay, and from blue to black, that's going to be a total of 6 for blue. So 6, 2, 4, and that will reduce to 3 over 2. Okay, for now we're doing something a little bit different because this is on a coordinate plane. You really can't count diagonally, so you need to count something that's vertical or horizontal. So I only see one line that's vertical, so starting at the blue, it's 4, and then the black is 2 units tall. Reduce it. Okay, same thing for the next one. Start with the blue, and you need to start with a vertical or horizontal distance. And that's 3, and the black is 2, and that does not reduce. So for scale factor, just pay attention to order, whichever way they say. If they say smallest to big, or big to small, or if there's a certain color compared to another one, like we did. Okay, almost done. This is 9-7, this is tessellations. So basically a tessellation is just a repeating pattern of figures that completely covers a plane without gaps or overlaps. So if you look, there's no spaces in any of these examples, and all together, it should form 360 degrees. Okay, and there's a gap here, so that would not be a tessellation. And there's also no overlapping. Okay, so how we can see if a regular object tessellates. So this is going to bring back that stuff that we did in Chapter 6 using the formula 180 times n minus 2. First of all, if we have a regular 18 gone, and we want to know if it tessellates, we need to figure out how many degrees are in one of those angles. So we're going to do 180 times n minus 2, and n in this case is 18. And then to figure out how many degrees are in 1, we're going to divide that by the number of sides. And the reason we're allowed to do that is because it says regular. And that is 160. So all of those interior angles need to add up to 360. So basically, is 360 divisible by 160? It goes into it 2.25 times, which is not a whole number, so that's not going to work. So let's try the ones below. We really just need to find, because these are all regular, we need to find one of the interior angles and see if it goes into 360. So an equilateral triangle, find out how many degrees are in one angle. You should probably just have this memorized, or you can use the formula. So an equilateral triangle, it has 60 degrees in one angle. Is 360 divisible by 60? Yes, it goes into it 6 times. It's a whole number, so yes, this does tessellate. Okay, let's try a regular octagon. Probably need the formula for this one. Go ahead and figure out how many degrees are in one angle. There's 135 degrees in one angle, and then we need to see if that goes into 360 an even amount of times. Okay, so it does not go in nicely, so that's not going to tessellate. Go ahead and try the next two on your own, and then play the video when you're ready to see the answers. Okay, so square. How many degrees are in one angle of a square? Should be 90. 90 divides into 360 4 times. So that's a nice even number, so yes, it does tessellate. Regular hexagon. Figure out how many degrees are in one angle. So there's 120 degrees in a regular hexagon angle, and we need to do 360 divided by 120 to see if it tessellates. And 360 does go, or is divisible by 120. So yes, it does tessellate. Okay, that's it. So if you have questions, let your teacher know.